Dear friends, we are getting ready to start the public lecture by Professor Ashoke Sen. May I request all of you to keep your mobile phones in silent mode. So I would like to request Professor Ashoke Sen and Director of IIT Bhubaneswar, Professor Shreepad Karmalkar, to kindly come to the stage. I would like to request Professor Karmalkar to extend warm welcome to Professor Sen with a flower bouquet. So we are all very happy that many of the participants from IIT Bhubaneswar and from various schools and colleges in Bhubaneswar, including several members of the participants of the Indian Strings meeting, including Indian and foreign participants who are here today. As you might be knowing, IIT Bhubaneswar is currently organizing the Indian Strings meeting from 9 to 14 December. And we are very happy to have a leading figure in theoretical physics, both within India and in the world, Professor Ashoke Sen, with us today evening, and I hope all of you will enjoy his lecture. He will be introduced shortly by Professor Debashis Ghosal. Before starting, may I request our director, Professor Karmalkar, to please come and say a few words to the participants.
It is my pleasure to extend a warm welcome to Professor Ashoke Sen and also to all the members of the audience. I see that there is a large number of school children, and it is only apt that they get interested in these things. This is the right age for you to get interested in the aspects that will be covered in the lecture. So I just want to have throw a very short question to the school children who are here. How many of you are aware that our Constitution says, one of the things the Constitution stipulates is that we must build scientific temper among the citizens. How many of you are aware of this? I am talking about school children. Okay, do I see some hand going up? Yeah, please raise it if you know. Yeah. So very good, at least some hands are going up. If not, there's an opportunity for you to know that much like we have studied in our civics courses in the school about what are our duties as citizens, one of the things is also the fact that we must build scientific temper, and all of us should be aware of it, right? So, talking about scientific temper, scientific method, can one of the school children tell me what are the key elements of scientific method? Anyone? We're just going to have a short interaction and then we're going to listen to Professor Ashoke Sen. Can anyone just stand up and tell me what are the key elements of scientific method? I'm sure many of you know it. You're just hesitating. I can pick people. So let me know here, which school are you from? All of you here? Sorry? Okay, good. Any one of you, can you please stand up and just tell me, what are the key elements of scientific method? It doesn't matter you make a mistake, right? We just want some response. Should not be just passive, right? So what are the key elements of scientific method? All of you have written records of experiments and so on, I'm sure, isn't it? How many of you have written records of experiments? Please raise your hands. Come on, you can't say no. I'm sure all of you have done experiments, right? Yes. So tell me, what are the things that you wrote in the record? Now, probably this is a simpler question. Same question in a different form. Anyone, please stand up and tell. Even from that end, because I saw hands going up in the beginning that you are aware of what does the Constitution say. Yes. Please, please go there and give him a mic. So I'm just warming the audience up to receive the main message.
Good evening, sir.
Yeah, tell us which school are you from, and then tell us your name, which school and which standard, and then you answer the question.
I am Abhijit Swai of 11th standard and from Cohen International School, Jatni, Khodda.
Okay.
So the key elements like aim, first of all the aim, the things needed, the steps or the experiment or the observation, and in last the conclusion, I think.
Right. Okay. Anybody else? Now that one answer we have got, let me get at least one more answer. Yes.
Good evening, sir. I'm Sashwata Swagati Biswa from Cohen International School. As I think that the first step we need to do is, first we should observe and ask question to ourselves. Then we should research about it and get some questions what it can be. And thirdly, I think we should do the experiment to know the actual conclusion.
Okay, sit down.
Thank you, sir.
Right. Now, it is interesting that none of you mentioned theory as a very important part of the scientific method. Right? And today's talk is about the theory. So, please remember, the key elements of scientific method, as some of you have pointed out, first there is observation, then there is an hypothesis, because you want to explain the observation. Right? So, it's an imaginative guess about how things work, how things may be working. And this hypothesis, very often scientists translate to some sort of a mathematical equation. And now you do an experiment to test whether your hypothesis is correct. And then what comes out of this, if the hypothesis is correct, then you get what is called the theory. So theory is a very, very important part of scientific method. Please note this. Without theory, you cannot say that something is scientific. There are other things like a thing should be measurable and so on. But today we are focusing on theory. So I just want to warm our audience up to that. That is one of the key aspects of scientific method. And what does the theory do? It helps you to integrate observations. Gravitational theory. What does it do? It integrates the fact that an apple is falling on your head, maybe in a straight line, and planets are going around the sun in whatever form of motion. The motions may appear different, but they're all governed by the same set of laws, right? Or same theory. So theory is one of the key elements of scientific method. It helps you to integrate your observations, point number one. Point number two, helps you to predict. How can you send something to the moon? You have to make calculations. And then ensure that you are designing a satellite that can go to the moon. Okay? So it helps you to predict. Explain and predict, these are at least the two elements of scientific, explain, integrate, observations and predict. So, and usually the theory has two parts, qualitative and quantitative. Qualitative means without equations, the basic idea is logical reasoning and so on, and then this translated into equations. So qualitative part and quantitative part. I think these are few things that all of us should know, whether or not we pursue science or engineering later on as school children, right? Okay, and I think we are all waiting to hear Professor Ashoke Sen talk about the string theory, which is trying to integrate different areas and probably come up with theory of everything. Okay? Thank you.
I would like to request Professor Debashis Ghosal from JNU, please come to the stage and introduce the chief.
Good evening to all. My pleasure and privilege to introduce today's speaker, Professor Ashoke Sen. But before I do that, I'd like to extend a very warm thanks and words of gratitude to the host institutes, IIT Bhubaneswar and NICER, who are organizing this strings conference that Chandra mentioned. We are here for that. That is how Ashok happens to be here to give this talk. It's a tall ask to introduce Ashok. You could Google, and I could probably have asked ChatGPT or something to write an introduction. It would have probably done a better job than I can do. But let me give some chronology. Ashok was born and grew up in Kolkata, West Bengal, and he went to the Shailendra Sarkar Vidyalaya school until his 11th standard, which was the final school year at that time. Then after that, he went to the Presidency College, Kolkata, from where he did his undergraduate BSc degree with an honors in physics. Then he went to IIT Kanpur, from where he did a master's, and afterwards he went to do a PhD from State University of New York, Stony Brook. And after that, he has been postdoc at various places, Fermilab, at SLAC at near Stanford University. Then he came back to India and joined the Tata Institute of Fundamental Research, where he worked for several years before joining the Harishchandra Research Institute, Allahabad, which is now known as Prayagraj. After his retirement from HRI, he is now a distinguished professor at the International Center for Theoretical Studies in Bengaluru. Ashok is also adjunct faculty at various institutes and has been visiting professors at many different institutes all over the world. He is most known for his seminal contribution to string theory and more generally in high energy physics. He is one of the leading theoretical physicists of our times and has been awarded many of the most prestigious awards in India and abroad, and some of them are the GD Birla and EM Birla Prize, the Shantiswarup Bhatnagar Award, the Dirac Medal and ICTP Prize, and the Breakthrough Prize. Actually, the first year it was introduced, the inaugural Breakthrough Prize and the inaugural Infosys Prize. He is also the recipient of Padma Shri and Padma Bhushan, and the Dirac Medal also from ICTP, among others, which is too numerous to list. If you Google, you will find that it mentions 3 topics in string theory in which he made really big contributions, and these are the areas of string field theory, duality symmetries in string theory, and tachyon condensation. But these are not only the areas in which his work is limited. In fact, his PhD work started with work in strong interaction physics, in particular aspects of quantum chromodynamics, and those papers are also very highly cited and used by researchers even today. But in the subjects in which he is most known, that Google thinks that he is most well known for, maybe not in the order of importance, because citations don't tell everything, but he has over 300 papers in all together in his career, 300 odd papers with 32 or 34,000, I think more than 34,000 citations, with an average of about roughly 110,000 citations. So that's actually a very remarkable achievement. Uh, but behind all this is a very warm and genial person who anyone can approach without being feared of a strong personality that he may not entertain questions, is too famous or something. He is always available to the students and almost anyone who would like to approach him. In fact, the organizers told me that I should tell some anecdotes. And the reason I have been asked to introduce him is that I was amongst his first students. Actually, the first, if you count two people who joined together on the same year and finished at the same day. The other person is Professor Sudipta Mukherjee, who is at the IOP Bhubaneswar, also here. So that's the reason we were introduced. And I don't think I would have been a student of Ashok if I had known that he is so famous. But it just so happened that he joined only a few months before I joined the Tata Institute in Bombay. So I didn't know about this very famous person. And in those days, in fact, it would be hard for you young people to believe that there was no internet. So we couldn't Google people in advance, and I was very, very ignorant. So I didn't really have to gather courage also to go and ask him. So I just happened to end up being his student. It was my good fortune. But in physics, we strongly believe in conservation laws. Momentum is conserved, energy is conserved. If energy gains somewhere, it has to lose from some other place. So my good fortune is Ashok's big misfortune to have me as a student. Then anyway, I have survived until now. He has some really good habits that the young students may want to emulate. He's very systematic and has a very good memory, of course, but he keeps meticulous record. Professor Karmalkar was mentioning about keeping records when you study science. And he has maintained records of all his calculations in thick notebooks, numbered sequentially from, I think, from his postdoc days, if not even earlier. And these are into several hundreds now. And he has kept all of them. So if you ask something, in principle, he can go back and dig out some calculation that he has done 30 years ago. So that's one of the characteristics. And the other is, we were colleagues. He was also at HRI, I was there. So we watched him closely. We were colleagues in Allahabad, and Allahabad didn't have an airport all the time. So the most common way of commuting from and to Allahabad was by train. And these trains, because Allahabad is in the middle of the country and the railway lines are not the best. So these trains used to be very, very late, run late by several hours, and we wouldn't know in advance. So you go to the train station, you find that your train is delayed by 6 hours or 8 hours or something, and that's only a rough estimate. It could have an error bar of 4 or 5 hours after that. So most of us would, waste time. We would go and have tea and curse the railway system, how badly they are maintained, why people can't do their work properly, and all that. Ashok would just quietly sit on his suitcase, take out his notebook, one of the number 351 or something, and then do his calculations and quietly finish doing some calculation that he was doing, and maybe start something new and maybe even finish if the train is too late. And this was corroborated by Professor Sudhakar Panda, who was the director of IOP and NICER, and retired from NICER recently. He was reminding me yesterday that a couple of occasions he traveled between Bombay and Bhubaneswar by train, where Sumati, Ashok's wife, used to work at IOP and Ashok was at TIFR. So they would travel by train, and this train was used to take 36 hours if it went on time. So Ashok would simply go up on the upper berth and take out his notebook number 105 and do his calculation, and this 36-hour journey was sometimes long enough for him to finish calculation that could be written up in one paper. So on one occasion, he actually did so, and when he got up got off at Bhubaneswar, Sudhakar asked what he's trying to do. He said, oh, he'll just go back to the institute, sit at a computer and write down what he has calculated. He's finished his calculation. He was very happy. But of course, he liked these journeys. He enjoys food. So he would entertain almost all the chaiwalas and all the other sundry snacks vendors to keep his energy going. In fact, one of Sudhakar's theorem was that everything that Ashok consumes in the form of samosas and biryani and all that comes out in Nuclear Physics B, which is one of the leading journals in high energy physics, or used to be one of the leading journals in high energy physics. These are among his interests, that is cooking, good food, and apart from physics, and reading books, and occasionally, reading books of various kinds, but occasionally also he indulges in things like barbecue, which we greatly enjoyed at HRI, and he would take really strong interest in that. For several hours we would marinate the food and then go and grill, and this was a big occasion in HRI. So apart from his research, he is very good teacher, and several of his lectures are available on the internet, on YouTube. You can go up and learn from them. But beware that when you listen to them, they sound really simple, but you should also do the background work, do some exercises. Otherwise, you'll find that whatever he has said is not so simple after all. It takes much more work than that, because the simplicity comes from his deep insight and experience over the years. He used to like playing cards, and that was one of his passions during his days in undergraduate and in IIT Kanpur, but he has since given up because that takes too much of time. Since I was asked to tell anecdotes, I will tell one anecdote before I finish. So this is about, he's known to be very, very patient, but this is about the limit of his patience. So he taught quite regularly at TIFR, and one occasion, this was a few batches after I had our junior, he used to give us open-ended exams. So the exam would start after lunch at around 2 o'clock or something, but you could take as long as you like. There were not too many questions, only 5 or 6 questions, but and you could answer, I think, 4 or 3 or 4. But they were tough, they required some thinking, and he would be willing to give you as much time as you need. So you would have dinner break, then you would have a tea break again, and so on. So people would just try for 6-7 hours, and then eventually whatever they could do, they could finish and give up and go. But on one occasion, this batch, now this guy is a very well-known experimental physicist in a very big institute in India. I can't name him. So he, being an experimentalist or a budding experimentalist, wanted to test Ashok's patience. So whatever he could write, I think he had finished by around 6 p.m. And he was not writing anything. He just wanted to know how long Ashok is willing to wait. So he kept waiting and waiting. Eventually, everyone submitted their papers by about 8 or 9 p.m. and went home. This guy is just sitting there and not writing anything. He wanted to know who blinks first. So at around 11 o'clock, Ashok finally gave up and said, do you want to write anything more? So he said no, submitted his paper and went. So that's him, even though his patience may have grown since then, it may have just almost reached infinity now. This is the anecdote that I wanted to. Thank you for your patience. Ashok.
Thank you, Debashis, for a very nice introduction. So we can now begin the public lecture by Professor.
the invitation, and it's a great honor for me to give this talk here. And I also thank Debashis for the introduction. For student, as he said. So today I'm going to talk about string theory and its many manifestations. So let me begin by saying what string theory is. And as we can describe string theory as an attempt to describe question as to what are the basic constituents of matter and what are the properties of this constituent. Okay. So the basic building blocks are the molecules, but molecules themselves are made of smaller blocks called atoms. Each atom in turn is made of a central nucleus and then a cloud of electrons that move around the nucleus. We also know that each nucleus is made of protons and neutrons. So we have a small core which is made of protons and neutrons, that's the nucleus, and then there's a cloud of atoms around the nucleus. But when we probe further, we find that even the protons and neutrons are made of smaller constituents called quarks and gluons. Electrons, as far as you know, are still elementary constituents. Okay, they cannot be broken any further. And it turns out that while quarks and gluons, at least according to our current understanding, are still elementary objects, elementary particles, there are in fact many other elementary particles, which we can call the zoo of elementary particles. And I'll describe the zoo in a few minutes. So this is what the current understanding of the structure of matter is. That there is a zoo of elementary particles, and a subset of that zoo of elementary particles make up all that we see in nature, okay, in the form of quarks, gluons, and electrons. Now, these elementary particles are not inert, they exert force on each other. Okay, we said that they interact, and they interact by various kinds of forces. Okay, and perhaps all of you are familiar with the gravitational force. Okay, this is the reason why we stay on the surface of the Earth, why Earth moves around the Sun. There is also electromagnetic force. You probably have all experienced the force of a bar magnet. Okay, but besides that, most of what we observe today is due to electromagnetic force. Okay, even the light that you see is the result of electromagnetic force. But besides this too, we also need to postulate strong and weak force for explaining the properties of these elementary particles. For example, the strong force is needed to bind the protons and neutrons inside the nucleus, or the quarks inside the protons and neutrons. And finally, there is weak force, which again we need to postulate in order to explain the force between these various elementary particles. So these forces give rise to complicated interaction between elementary particles. And these interactions are typically measured by studying how the elementary particles scatter off each other. Okay? And this is where the experiment comes in. Okay, as you heard, the beginning of a scientific discovery or scientific inquiry is that you make observations, okay? And these observations for elementary particles take in the form of this scattering between elementary particles. What happens when you throw two elementary particles towards each other? Now it turns out that the effect of gravitational force between elementary particles is negligible compared to the other forces. So the gravitational forces cannot be measured by standard scattering experiments because they don't really affect the standard scattering experiments very much. They have to be measured by other means, like, for example, that the Earth and the Sun exert gravitational force on each other. Okay, then that's the reason why the Earth is going around the Sun. Now, to see that the gravitational force is small compared to the other forces, okay, one can do a simple calculation, and this is the only calculation that I'll be doing in this talk. So you can compare the electrostatic force between two protons with the gravitational force between two protons. Okay, and for simplicity, we can imagine that both protons are at rest so that we can calculate the forces very easily. So here is a formula. We calculate the gravitational force between two protons by looking at by using the Newton's law of gravity. okay, where G here is the Newton's constant, mp is the mass of the proton, and by the inverse square law, the force takes this form, gmp square over r square. And similarly, the electrostatic force between two protons can be calculated by using the Coulomb's law, okay, which I have written here. And in this calculation, I am using CGS units because that's what I learned in school, but you can use any other units that you like. But the ratios of the forces, of course, is independent of what units you choose. Okay, it's a dimensionless number. And when you put in the values, okay, which I have done here in the electrostatic units, you find that this ratio is an extremely tiny number, like 10 to the minus 36, and that's what shows that the gravitational force is small compared to the electrostatic force. And similarly, all other forces are also much larger than the gravitational force. Okay. So as I said, because of this, the gravitational force cannot be calculated using the direct scattering experiments. Okay. You have to study gravitational force by looking at the force between very, very massive objects. So this is what we know from experiments. Okay, the existence of these various forces, the existence of various kinds of particles, and how they interact via these forces. So now we want to develop a theory for this. Okay, the theory will tell us what lies behind the elementary particles and the forces that they exert. And to develop such a theory, we have to remember two important points. First is that in typical experiments, elementary particles move very fast, almost at the speed of light. So we need to use what is called the special theory of relativity, which is the theory that describes particles which move very fast. The second thing we have to remember is that the elementary particles are very small, and because of this, we cannot use the standard classical laws or Newton's laws of motion for describing elementary particles. We need to describe them using what is called the quantum mechanics, okay, which requires some modification of the Newton's laws. Now it turns out that there is such a theory which has in fact been so successful that we call it the standard model. So this theory is based on the principles of quantum mechanics and special theory of relativity. And in principle, this theory can be used to calculate the result of any experiment that you use to perform involving elementary particles. And so far, the standard model indeed has been extremely successful in explaining almost all observed experimental data involving elementary particles. However, there is one shortcoming of the standard model, that it does not include gravity. Now, even though it does not include gravity, as I said, it is well suited for describing scattering between elementary particles, because as you saw, the effect of gravitational force is very, very small during scattering of elementary particles. Nevertheless, standard model by itself cannot explain why the Earth and the Sun exert gravitational force on each other, even though both the Earth and the Sun are made of elementary particles themselves. So here I have given the list of elementary particles according to the standard model, and this is what I meant earlier by the zoo of elementary particles. So they are divided into various classes, okay, which I have called quarks. As you can see, there are several types of quarks. In fact, 6 times 3, which is 18 types of quarks, okay, which we call the up quarks. And these 1, 2, and 3 sometimes is also referred to as colors, red, blue, and green, but those are just names. Okay, it's just enough to know that there are 3 kinds of up quark, 3 kinds of down quark, 3 kinds of charm quark, 3 kinds of strange quark, 3 types of top quark, and 3 types of bottom quark. So there are various kinds of quarks, of which protons and neutrons are made of only essentially the up and the down quarks. Then there are particles called leptons. Here you see the familiar electron that I introduced earlier. Okay, this is called the neutrino or the electron neutrino, and there are similar particles which are listed here. This third group is an important group of particles. These are the ones that are responsible for the forces. So for example, the gluons, okay, there are 8 particles collectively called the gluons. These are responsible for strong forces. So the reason that two particles exert strong force on each other is that they keep exchanging gluons among themselves. Similarly, photon is what mediates electromagnetic force, and these are the particles that mediate the weak force that we mentioned. And finally, there is a particle called the Higgs, okay, which apparently plays no role like these. Okay. Nevertheless, this is absolutely essential in order to have a consistent theory of elementary particles. Okay, the standard model will not succeed without having this Higgs particle. And here I should mention that the Higgs particle was predicted just based on the theory about 50 years before it was actually discovered. The discovery of Higgs goes back to 2012, but its existence was predicted long time ago, just based on theory. But by now, we know all the particles, we have experimentally seen all the particles that are listed here. So it is very successful. Standard model has been quite successful in explaining, as I said, the elementary particle scattering. However, despite its success, we know that the standard model cannot be the final story. First of all, there are some experimental results which do not agree with the predictions of the standard model. So for example, according to the standard model, the neutrinos that we saw are supposed to be massless particles. They have no mass. According to the standard model, these neutrinos have no mass. But we know now from experiments that the neutrinos do have small masses. Okay, so we have to modify the standard model. But it turns out that these can be easily explained by a somewhat minor modification of the standard model without giving up any of the basic principles of the theory. There is, however, a more serious reason why the standard model cannot be complete. And as I have already said, that the reason is that it does not contain one important force that we observe in nature, namely the gravitational force. So let me repeat again that the gravitational force is not measured in scattering between particles because it's too small. Okay. Nevertheless, we know that it exists because big objects do have gravitational force. So if we have a theory that is based on the standard model, that theory cannot explain why, for example, the Earth and the Sun exert gravitational force on each other. Okay, so we have to modify the standard model. So this is, in fact, what we can call the experimental input for the starting point of string theory. So string theory is an attempt to combine gravity with standard model to get a complete theory of the universe. So given that standard model does not contain gravity, okay, the next question will be, is it possible to modify the standard model so as to include gravity? And for this, recall that the standard model is based on the principles of special theory of relativity and quantum mechanics. So we need to first make the theory of gravity consistent with these principles, okay, because only then we can hope that we have a combined theory of the strong, weak, and electromagnetic force and gravity, and that will be the complete theory of the universe. Now the first step, that is making gravity consistent with special theory of relativity, this was carried out by Einstein in 1915. And this led to what we now call the general theory of relativity. When the theory was first formulated, it was quite esoteric. Okay, very few people understood it. Okay. By now, we have, of course, enough tests of general theory of relativity, okay, and we also have practical applications. Okay. For example, the GPS system requires that the clock on the Earth has to be synchronized with the clock on the satellites, and there, unless we take into account the effects of general relativity, you will make a mistake. Okay. So general relativity is crucial in making sure that the GPS system works. Okay, so general theory of relativity is quite successful, okay, but at a level of classical physics, not quantum physics. So that is the second step. Okay. That is, we have to somehow modify the general theory of relativity so that it becomes consistent with the principles of quantum mechanics. And this turns out to be an extremely difficult task. And this is where string theory comes in. Okay, string theory turns out to provide a possible way out of this problem. And as we will see, it also provides a possible way of combining a theory of gravity with the theory of elementary particles. So let me recapitulate again. Okay, so currently, experiments tell us that we have gravity, we have quantum mechanics, we have strong, weak, and electromagnetic force. And now the job of the theory is to try to find a consistent mathematical framework that can describe all of these. So with this, let me say what string theory is about. In fact, string theory started its life not as an attempt to formulate a theory of gravity, but for something completely different, which I'll not describe today. But the basic idea of string theory is that different elementary particles, or what we think of as constitute particle-like objects which constitute matter, are in fact different vibrational states of a string. Okay, it can come in the form of closed strings with no ends, as you can see here, or open strings with ends. So again, the idea is that the elementary constituents of matter are not point-like objects, but string-like objects. Okay. And the different vibrational states of the string should act as if they are different elementary particles. So if string theory is successful, okay, then all of these particles that you saw here, they should all correspond to different vibrational states of the string. Okay, that's the main idea behind string theory. Okay, so if this is the case, then the next question that would arise is, if the elementary objects are really string-like objects, why haven't we seen this? Because in all experiments, elementary particles appear to be point-like electron appears to be point-like, quarks appear to be point-like, and so on. And the answer to this is contained within string theory itself. What one finds is that the typical size of a string, in fact, is extremely small. It's of the order of 10 to the minus 33 centimeter. And this is much, much smaller than the length scale that we can probe by any present experiment, which in fact is of the order of 10 to the minus 17 centimeter. And because of this, even if string theory was right, to any present experimentalist, the states of the string will appear to be particle-like objects. But this also tells us that there is a clear prediction of what string theory should give, that if we could probe distances, okay, which are of this order, which are of order of 10 to the minus 33 centimeter, then you should see that the elementary particles actually behave like strings, that they are one-dimensional objects rather than zero-dimensional objects. It's just that with our current experimental techniques, we cannot probe distances that are this small. Okay, but this, of course, doesn't mean that this cannot be done in the future. So we need to formulate a theory of strings, and as we have already emphasized, that this has to be consistent with the principles of quantum mechanics and special theory of relativity, because these are experimentally verified principles. And it turns out that as a consequence of these two requirements, strings automatically exert gravitational force on each other, which means that one of the vibrational states of the string has a property that appears as an elementary particle that acts as a mediator of gravity. Just like we saw photons as the mediator of electromagnetic force and the gluons as the mediator of strong force, and the W plus, W minus, and Z as mediators of electromagnetic of weak force, string theory automatically gives rise to an elementary particle that mediates gravitational force. And if you recall, this particle was absent in the list that I showed you, because standard model doesn't contain gravity. Furthermore, as I said, this theory is automatically consistent with the principles of quantum mechanics and general theory of relativity. So in this sense, string theory already gives you a consistent quantum theory of gravity. The main question now is, does it also include the strong, weak, and electromagnetic force that we are familiar with? But before that, let me just say that the string theory is based on these principles, but it turns out that it's very, very tightly constrained. It's so tightly constrained that we cannot adjust string theory to suit our needs. Okay? We cannot change the laws of string theory, and this is very different from the laws that govern the theory of elementary particles, okay, where we can modify the theory, okay, often according to what we wish to do. Just like I said, in the standard model, neutrinos have no mass, but we can modify the theory to accommodate mass of the neutrinos. Okay. These kind of modifications we cannot do for string theory. Okay. So we cannot demand even that the dimension of space is what we observe in nature. Right? We are all familiar with the fact that we live in 3 space dimensions, but this we cannot demand of string theory. We have to just take what string theory gives us. Or we cannot demand that different vibrational states of the string behave like the elementary particles we observe in nature. If string theory gives it, it's well and good. If it doesn't, then we are out of luck. So basically, you have to take what string theory gives us. So let's now see what string theory gives us. First of all, one finds that there are 5 consistent string theories, and these differ from each other in the way the string vibrates. Okay, this is a technical point. Okay, there are clear mathematical equations which distinguishes these 5 different string theories, but I'll not write those equations here. Furthermore, one finds that in each of these 5 string theories, the dimension of space is 9, which may be hard to visualize. What is a 9-dimensional space? It basically means that we require 9 coordinates to describe a point in space instead of the usual 3 coordinates that we use to describe a 3-dimensional point. But this certainly is not what we see in nature, right? As we discussed, we see 3 dimensions in nature, up and down, left and right, and front and back. So how can we reconcile string theory with what we see in nature? Now it turns out that there is an old idea called compactification that can be used to make an intrinsically 9-dimensional theory appear as if it's a 3-dimensional theory. And I'll try to explain this using a simpler example where we will consider an imaginary world which has only 2 dimensions, and I'll explain how that 2-dimensional world can be made to look as if it's 1-dimensional. So let's consider a 2-dimensional world with 2-dimensional people living in it. Okay, so you can imagine that flat land which extends to infinity in both directions. Okay, and imagine that the creatures which are 2-dimensional, they can only slide along that flat land. Okay. But now we are going to make this a little more interesting. Okay. We'll take this flat land and we'll say that it's not infinite in all directions. In one of the directions, okay, if you travel a certain distance, you come back to the original point. Pictorially, you can think of this as what you see as the surface of the cylinder. Forget about the interior of the cylinder. Imagine an infinite cylinder and consider its surface, which the cylinder is of radius r. So, on such a cylinder, if you walk 2 pi r distance in one direction, you come back to where you started. So, if we look at the surface of the cylinder, we can see that if r is very large, say larger than the range of the most powerful telescope that these 2-dimensional creatures might have, then the 2-dimensional space will appear to be infinite in both directions. So imagine that in our units, r was, say, 10 million light years. Okay, then probably we will not realize that this space has this periodic structure. We will think of this as an infinite space. Now you can consider the opposite situation where r is very, very small. Okay, you can see it here. And perhaps you can visualize that if r becomes smaller and smaller, then this world looks more and more like a 1-dimensional world. Okay. And indeed, in the limit of r goes to 0, okay, we can really think of this as a 1-dimensional space. Okay. And if r is, you don't really have to take it to 0, as long as r is smaller than the resolution of the most powerful microscope that these creatures might have, the world will appear to be 1-dimensional to the people living in this world, because they will not be able to see the existence of this extra dimension where it's too small to be observed in a microscope. So this is the physical picture by which, even though a space may be intrinsically two-dimensional, a point on this space requires two coordinates to describe it. Right? One along this and another one along the circumference. Okay? For sufficiently small r, the coordinate that specifies the distance along the circumference becomes irrelevant. Okay, we don't really need it because you don't see that direction microscopically in any microscope. And effectively, one coordinate is sufficient, and we'll be led to believe that we are living in one dimension rather than two dimensions. And it turns out that the same idea works in making a 9-dimensional space look 3-dimensional. We can take 6 of the 9 space directions to be small, which describes some compact space K. And the idea is that when the size of K is sufficiently small, then the space will appear to be 3-dimensional, and that's the way the 3-dimensional world emerges from string theory. Now, mathematical consistency. Okay, again, this is something I'll not be able to explain what are the mathematical consistencies, but it turns out that demanding that the theory is mathematically consistent, it puts strong restriction on what kind of spaces K that we can use for compactification. Not every space K can be used. Okay. Nevertheless, there are many different spaces for which that we can use for compactification. These are 6-dimensional spaces, because recall that we have to we have to make 6 of the 9 space directions to be small and compact. Okay, that's what we're calling K. So there are many different choices of this 6-dimensional space. And so this says that even if we begin with a specific string theory, okay, one of these 5 consistent string theories that I described, okay, that once we allow this compactification, there are more possibilities because there can be different choices of K. And one way to regard these different possibilities is as different phases of the underlying string theory. And this is what I'll try to explain in the next few slides. What do you mean by different phases of string theory? So for this, I'll use an analogy. You are probably all familiar with the fact that ice, water, and steam, they all are described by the same molecule, the H2O molecule. So if we have a theory that describes the H2O molecules and the force between the H2O molecules, then that single theory can have different manifestations, and those different manifestations are what we call the different phases, okay? And they are ice, water, and steam. So we say that ice, water, and steam are the different phases of the theory of H2O molecules. So when I say that the string theory has many phases, it's exactly in the same spirit. These different choices of K, okay, which are possible, correspond to different phases of string theory, just as ice, water, and steam correspond to different phases of the theory of H2O molecules. And just as the environment inside ice, water, and steam are very different, similarly, the 3-dimensional environment for different choices of the compact space K will be very different. Okay. So if K takes one shape, okay, you will see one kind of environment in the 3 dimensions. If K takes a different shape, okay, you will see a different kind of environment in the 3 dimensions. Just as ice and water have very different manifestations. And indeed, even the fundamental constants of nature, or what we believe, okay, from the standard particle physics viewpoint as fundamental constants of nature, like the number of elementary particles and the masses and the charges that the elementary particles carry, will appear to be different in different phases of the theory. Okay, and that basically says that these are not really fundamental constants of nature. Okay. They are constants that we can in principle compute once we know which phase of string theory that describes us. Now it turns out that for some choices of K, the 3-dimensional environment is very similar to the nature that you observe. It has elementary particles and forces similar to what you observe in nature. Particles like the electrons and neutrinos and quarks and gluons and photons and W particles. And this basically says that besides solving the problem of formulating the quantum theory of gravity, string theory also offers the possibility of combining this with the theory of elementary particles and their forces. Okay. Now note that here I have said that it offers the possibility of combining this with the theory of elementary particles and their forces, but this requires that you have to find a particular choice of K, this 6-dimensional internal space, that gives exactly the kind of elementary particles and forces that you observe. Okay? Not the qualitatively the kind of elementary particles and forces that you observe, but it should have quantitative agreement with the kind of elementary particles and the forces that you observe. In particular, the mass of the electron should be exactly what you observe in nature. Okay? The mass of the quark should be exactly what you observe in nature, and so on. So this remains an open problem. So far, you have not found a phase of string theory that has exactly the elementary particles that you observe in nature, and this remains an open problem. And in fact, in this conference itself, there are several talks which describe various attempts to try to circumvent this problem. Okay? Basically, trying to find more and more phases of string theory with the hope that someday we'll land on a particular phase that has exactly the kind of elementary particles that you observe in nature. But this is still an open problem in string theory. Now, the analogy between different phases of string theory and different phases of H2O in fact goes further. Okay. And so let me explain what I mean by it goes further. So let's suppose that you are living inside water and you wanted to study the properties of ice. We know how to do it. We will have to just freeze a part of water into ice. We have to spend some energy to do that. Nevertheless, we could freeze a part of water into ice and do our experiments on ice. Right? So even though we are living on water, we can study ice, and that's because water and ice are different phases of the theory. And it turns out that we can also do similar manipulations with the phases of string theory. So let's suppose that you are living in a phase in which 6 of the 9 dimensions are just circles of small size. I described a particular case where there is one circle. Okay. Imagine that each of the 6 directions are just small circles. Okay. That's a very simple choice of the compact space K. And suppose you are living in such a world. Okay. This will indeed appear to be a 3-dimensional world like ours because the 6 of the directions are very small. And now you can ask, living in such a phase, can we study properties of a phase of the theory in which all 9 dimensions are large? And it turns out that we can. And all you have to do this is to create a large black hole carrying appropriate charges in this 3-dimensional world. In that case, near the black hole, the space will open up into a 9-dimensional space, and we can send our instruments and study the properties of the 9-dimensional phase of the theory, just as in water, we can freeze some part into ice and send our instruments and measure the properties of ice. And we could even go and live there and experience the 9-dimensional world if we choose to do so. So here is a picture. Okay. So here is the 3-dimensional space. Okay. From far away, the world looks 3-dimensional. Okay. That's where, say, we are living. In this 3-dimensional space, we can create a black hole of appropriate charge and mass. And with this black hole, it turns out that as you approach the black hole, the dimension of the compact dimensions, okay, the sizes of the circles, become larger and larger as you go closer and closer to the black hole. Okay. And here, the sizes can be as large as you want. Okay. By adjusting the charge and the mass of the black hole, you can make the size as large as you want. You can make it, for example, 10 million light years, and that will be essentially indistinguishable from really 9-dimensional space. So you could live or do our experiments at various distances from the black hole and experience extra dimensions of various size, just as from inside water, we can study the properties of ice. Now, from what we have described so far, it would seem that there are altogether 5 consistent string theories, each with many different phases. And indeed, this was our understanding of the theory in the early days. However, subsequent research showed that these 5 different string theories are not really different, but in fact, they all give different descriptions of the same underlying theory. And what we mean by string theory today is this unified theory, okay, which encompasses all the 5 string theories that we started with. So here is a picture, okay, again it is a schematic picture. So different phases of this unified string theory can be schematically represented as a different points inside a room with 5 windows. So let's imagine that you have a room with 5 windows and there are these various strange names. Okay, these names are in fact the names of the 5 different string theories that I talked about. And so the idea is that inside this room there are different points which represent the different phases of the theory. And through each window we see only a small part of the room. Okay, so the points here describe this particular string theory and its various compactifications, okay, where you take some of the directions to be small and compact. Similarly, from this window, we see this theory and when some of the directions are small and compact and so on. And the idea is that if there is no overlap between the different parts that we see through different windows, then we will not know that we are looking into the same room. Okay, and this is what describes the situation in the early days of string theory. Okay. So in the early days, basically you could see only a little bit through each window. Okay. And so you would not realize that it's actually the same room. But as we developed our techniques further, we could see deep enough through each window, okay, still not the whole room from each window, but we could still see deep enough so that we realize that we are actually looking into the same room. And this is what is called the dualities in string theory. And that's what I have said here, that once we begin seeing deep enough into each room through each window, into the room, then we may get a glimpse of some objects through more than one window. And that's what leads us to realize that all the windows open into the same room, and that's what describes the situation now. But I should say that still we don't have a vision of the full room. Okay? And the idea is that we have only discovered a small amount of phases, okay, near each window. Okay? Maybe there is some overlap, but most of it is still undiscovered. And if string theory is right, and if it's capable of describing our world, it presumably corresponds to some phase hidden somewhere in the deep interior of the room that you have not seen so far. Okay? That's the basic hope of string theory. So one of the main directions of research in string theory involves attempts to open up new windows into this room. Okay, are these the only 5 ways of studying the theory, or are there other ways? And in fact, there are new windows. Okay, the most famous example of such a window is what is called the ADS-CFT correspondence. Okay. And it turns out that some phases of string theory may be actually described by quantum theories of point particles. So you can describe those phases by simply studying the theory of point particles. Another example of such a window is what is called the M theory, okay, that a particular phase of string theory may be described by theory in 10 space dimensions instead of 9 space dimensions. And I should just say that all of these phases can be created in the vicinity of appropriate black holes in the 3-dimensional phase of string theory that he described earlier. Namely, you start with a string theory with all 6 directions made into small circles, okay, and then by adjusting the charge of the black hole appropriately, we can ensure that as you go close to the black hole, you either see the M theory phase or you see the anti-de-Sitter phase, the ADS phase, okay, and you can study them in principle. So to summarize, the problem of connecting string theory to nature reduces to demonstrating that there is a phase of string theory that describes exactly the nature that you observed, and explaining why nature exists in this particular phase and not in any other phase. And both of these issues are currently under active investigation by many researchers. Okay. And here I should add that if we could do this, then we could have the full experimental test of string theory in the sense that we could actually predict the masses of elementary particles and the charges that they carry, the forces that it exert on each other, and so on. But if we cannot find such a phase, okay, that doesn't mean that string theory has no prediction. It has a clear prediction that if you collide particles at a very, very high energy, so that you probe distances of the order 10 to the minus 33 centimeter, then you should see string-like objects rather than particle-like objects. Okay, but you have to probe that deep to see the string structure. So I'll finish by describing a speculative solution to the second issue. Okay, let me remind you what the second issue was. Okay, and that is that even if we find a phase of string theory that describes exactly the nature that you observe, we have to explain why nature chooses a particular phase of string theory where we live, and why not any other phase. So according to this speculation, no single phase of string theory is spatial, and in fact different parts of the universe exist in different phases, and we see a particular phase of string theory just because we happen to live in a particular region. So this is similar in spirit to the mechanism that we described to create a 9-dimensional space in a 3-dimensional world. Right? Imagine that if you go back to this picture over here, okay, suppose you have a big black hole, then far away, if you live far away from the black hole, you see as if you are living in a 3-dimensional space. If you live close enough to the black hole, you see as if you are living in a 9-dimensional space. Okay, and in fact, by adjusting the charges of the black hole, you can have various other kinds of spaces that appear in the near the black hole. Okay? So, what kind of space you see, or what, it depends on where you live. Right? If you live here, you see one kind, you have one kind of experience. If you live here, you have a different kind of experience. So in spirit, this is similar. But for the type of phase that we need to describe the universe around us, the actual mechanism turns out to be a bit more complicated than just forming a single charged black hole. And this is what I'll try to describe. So it turns out that many phases of string theory have the property that they expand rapidly according to the laws of general theory of relativity. Okay? Technically, we say that they have large cosmological constant, but this is what is important, right? That those phases start expanding rapidly, and that basically means that given 2 points in space in such a phase of the theory, those 2 points will move away from each other very, very rapidly. Okay, every pair of points move away from each other very, very rapidly. And then once in a while, bubbles of new phases can form in different regions via quantum phase transition. Okay, this is again a technical word, but basically the idea is that you have a rapidly expanding phase, and once in a while, because of the effect of quantum mechanics, the other phases can start forming. Okay, bubbles of other phases can start forming, and they themselves start expanding. But typically, if you have such a situation in a liquid, I mean, this is very similar to the physics of a supercooled liquid. Imagine that you have a supercooled water, and you disturb it a little bit, pockets of ice start forming in different regions, and then they expand and collide, and they form, the whole thing becomes ice. Okay. Here, this would have happened, as the bubbles expand, the boundaries would have collided and made into a single phase, except that because of this rapid expansion of this intervening medium, okay, which is a consequence of general theory of relativity, it's a standard classical general theory of relativity, no quantum mechanics here. Okay. It turns out that these phases can get separated and never collide. So net result is that inside this rapidly expanding medium, different phases of the universe will form and fill up this medium. Okay, the medium will always be there, but they will keep forming as the universe expands, as this medium expands. And this process can continue for infinite time. Okay. And so it's possible that every phase of string theory will be realized in some region of the universe. Okay. And in such a universe, no phase of string theory will be spatial. Okay. But it's just that in different regions of the universe, we have different phases. And we see one particular phase because we happen to live in that region. So I'm almost at the end of the talk. Let me just describe what I call the side stories. So what I've described so far is what can be called the main story of string theory. But like all the great epics, string theory also has many side stories. And these involve possible application of string theory to solve problems in other related fields. And here are some examples. String theory has been used to understand black holes in quantum theory, which in fact had many puzzles which string theory has been able to resolve. String theory approach to solving problems in quantum field theory because of this strange relation between some phases of string theory with the theory of point particles. We can actually use string theory to study the theory of point particles. And of course, there are many, many applications of string theory to mathematics, okay, because of this strange picture. Okay, maybe I can describe this. Okay, that because of this featured that the same phase of string theory may be described from many different windows. Okay. We can compute some physical observed quantities. Okay. What the consequence will be we can compute from this window or this window. Okay. They give apparently different results. And then consistency of string theory requires that even though they look different, the result better be the same. And this leads to new mathematical identities that you calculate from this window and you calculate from this window, demand that the results are the same. And all those mathematical identities are new identities that were first predicted by string theory and then independently proved by mathematicians later. Okay, so this involves the application of string theory to mathematics. Okay, this is why string theory can actually say something new in mathematics. So all these make string theory a rich subject to study and explore. So let me now summarize. So what I have said, the string theory is an attempt to formulate a theory of nature that will explain the existence and various properties of all the elementary particles and their forces. It is based on the simple idea that different elementary particles are different vibrational states of a string. Just as a consequence of the simple idea, string theory provides us with a consistent quantum theory of gravity and possibly of other forces as well. Okay, this still remains an open question whether it can really do it. Okay, because for that you have to search in that box, okay, and try to find the particular phase that actually describes us. We also said that initially it was thought that we have 5 consistent string theories, each existing in many different phases. We now know that they describe different phases of the same theory. But finding a phase of this unified string theory that describes the world around us, that remains a challenging problem for the future. Thank you.
If you have any questions, please raise your hand.
Good evening, sir. My name is Alan. Sir, while describing that no phase is special, you gave some example of black hole and that it depends on how far we are from the black hole, no, sir? Sir, I understand it is an abstract concept, but I can't think of any other way that, are you suggesting that there is a black hole outside of our universe and that our universe is like a phase and it happens to be in the distance that we are experiencing 3D? And there could be, is it also suggesting that there could be other universes, sir? Like, that's not.
I'm not, as I said, for our universe, the black hole is too simple a picture. That was for a different kind of universe where the extra directions is just circles. We know that that simple phase doesn't describe our universe. Right? Our universe is more complicated. And so for that, we need this more elaborate picture that I described here. Right, that you need this rapidly expanding phase, and then inside this will be embedded in one part our universe. But indeed, as we go out, okay, we'll see that there are these other phases that exist in the universe. Okay, so the whole universe, in this picture, the whole universe contains different phases, and one of which happens to be our universe, our phase.
Oh, yes, sir. Thank you, sir.
So the black hole is a simpler version of this, right? But we know that that simple version doesn't apply to our universe because we are not living on a space, right? If you remember, okay, let me show you, that this applies to when the 6 of the 9 dimensions are each circles of small size, right? This is a very simple kind of compact space K, and we know that that is not enough to describe us. Okay, it's too simple. But if we did have a universe of this kind, then the black hole will do the job.
Yes, sir.
Good evening, and thank you, sir, for your nice and very new talk. For last few minutes, I'm facing very hard to understand your talk. In fact, I have not understand.
Okay?
Yeah.
Yeah, so which part do you want me to explain?
Just can you define what is string?
What is strings? Okay, string is a, let me go back to here. Yeah, so string is just a one-dimensional object like this, right? Imagine a closed string. You can think of the string that you are familiar with, right? You can take a rubber band, but almost zero thickness. The difference between a string and a rubber band is the rubber band follows the Newton's laws of motion. These strings are relativistic, they follow the laws of relativity. Okay, so the two things that distinguish a string from a regular rubber band is that they follow the laws of special relativity and they follow the laws of quantum mechanics. This is what I have said here, that you have to satisfy these two basic principles, but otherwise the string is like a rubber band. And this is what is supposed to be the elementary constituents of matter.
So can you tell how this string is different from other object, molecule or atom? How it is different?
Yeah, so molecules and atoms are composed of smaller objects, right? In string theory, each of these strings will be like elementary particles, and the molecules and atoms will be built out of these strings.
Okay.
Many strings together will form a molecule and an atom.
And another thing.
Yes.
Sir, you are talking about many dimensions, sometimes 3 dimensions, sometimes 6, sometimes 9.
Yes.
So that dimension, who is sensing? With respect to whose vision you are telling? It's human being or what? Like say for example, there are a lot of creatures who cannot sense 3 dimensions on this earth. That microorganism and other thing. And we, so far, 3 dimensions. 9, 6, 12, that dimension you are talking about with respect to whom?
Well, this is a mathematical description. Okay. If the dimension, let me here have explained. See, here for example, take the case of 2 dimensions. Right? Take the surface of the cylinder. If the surface of the cylinder if the radius of the cylinder is very, very large,
Yeah.
then a creature living on this will see it as a 2-dimensional world.
Yeah.
Now, when the radius becomes small, right, smaller than the sensory organs of the distance that the creatures can sense, or even smaller than the microscope that these creatures might have built, that's the picture here, then it will appear as 1 dimension. So intrinsically, this space is 2-dimensional. It has 2 coordinates. Okay? But it just so happens that depending on the size, it may appear as 1-dimensional to the people living in that space. So the same picture is true in string theory, that intrinsically string has 9 dimensions. Right? This is what is given by the theory and you cannot change it. Okay? But the theory allows some of these directions to be small and compact, okay? Just like this circle over here. Okay? And the idea is that depending on the size of the circle, size of those compact directions, we may either view it as a 9-dimensional space or a 3-dimensional space or even something in between. Imagine that some of the directions are large, some of the directions are small.
Yeah.
Then it may appear as 8-dimensional or 7-dimensional or 6-dimensional. That depends on the choice of this compact space K.
Another thing, simple thing, say for example on cube or sphere or cuboid, whatever. So do you think that is a cube exactly?
Sorry, I didn't understand the question.
Say for example, screen. What is the shape of the screen?
The shape of the string?
Yeah.
Yeah, see the string is vibrating, so it exists in many different quantum states.
No, sir, my question will come later. Just to answer my question, what is the shape of the screen?
See, string doesn't have a definite shape because it's described as laws of quantum mechanics, right? So you think of an atom. Does the atom have a shape? The electrons are a cloud of there is a cloud of electrons inside the atom, right? And described by the probability of the electrons being in different states, okay, different positions. The string is exactly the same. There is a probability of the string being this big or the probability of the string being this big. That depends on the particular quantum state of the string. In quantum mechanics, you don't talk about definite shapes. You only talk about probabilities.
Okay, sir, thank you. Actually, still I'm facing difficulty to understand this theory. Sorry, sir.
Thank you.
My problem. Okay. Thank you, sir. And sorry, sir.
Thank you, sir. Good evening, sir.
Yes.
I'm Paul Ram. I have two questions. One is, so you showed that the phases they emerge as bubbles.
Yes.
So do they also disappear? And so if they are disappearing and getting created, so you also initially talked about the conservation of physical quantities. So in this grand universe having 9 dimensions,
Yes.
is there again loss like conservation of whatever the quantities are? So that's one question, sir. And the second question is, so you mentioned about the compaction. So we are in one of the phases of this grand universe, whatever
Yes.
we may call. In the example of that Edwin about the flat land. So if we are living in that compacted flat land, can we actually sense the other dimensions? So how are we actually hoping to actually prove that we are in one of the phases?
Okay, yeah. So let me first start with the first question. So you are asking whether these phases can disappear, and they can disappear. They cannot just disappear. What can happen is that some other phase may form inside them. Okay? Just like in this rapidly expanding universe, we form bubbles of these phases. Right? Some other phase can form inside this, right? And that will all again start expanding inside this phase. Okay, that's the way the part of this phase may disappear. Okay? But they will not just disappear into nothing. Okay? And the conservation laws, this obeys of course all the conservation laws that are implied by the theory. But once you include the effect of general theory of relativity, the conservation laws are somewhat strange. Okay? Energy as such is not conserved, okay, because this medium has pressure, and that can change the total energy. Okay? But otherwise, it does follow all the conservation laws. Now about detecting the extra dimensions. Okay? So basically what you have to do, right, if you go back to this picture, imagine that you had these two-dimensional creatures, right, and they are actually living in this, on this cylinder. They are not being able to see this extra dimension. Okay? But if they start building better and better microscopes, okay, then eventually they will be able to see these extra dimensions. Okay? And in string theory, okay, the analog of there is a bound, there is a limit on how small these extra dimensions can be, and that is the same 10 to the minus 33 centimeter that I described earlier. Okay, that's a fundamental length scale. Okay, so you know for sure that the extra dimensions cannot be smaller than 10 to the minus 33 centimeter. Okay, so if you can build a microscope that is strong enough to see that, probe that distance, then you will indeed will see these extra dimensions. Okay, and if you don't see them, okay, that will basically show that again the string theory cannot be the correct theory, because string theory predicts the existence of these extra dimensions. So that's the way you have to see these extra dimensions, that build better and better microscopes. Okay. So today's microscopes can probe a distance of the order of 10 to the minus 17 centimeter. Right? So you have a long way to go, but it doesn't mean that eventually you cannot reach there.
Sir, so does it mean the quarks U1, U2, they are not actual objects but abstract things referring to vibrations of strings?
Well, vibrations of strings are also actual objects, right? But indeed, so according to this, the quarks, and if string theory is the right theory, then quarks and gluons will be some vibrational states of the string, right? It is the same string, but they are appearing in different ways of vibration of the string will appear. One way will appear as a quark, one way will appear as a gluon, and so on.
Sir, so what is the difference? The frequency?
Yeah, the frequency, the amplitude, right? In quantum mechanics, of course, you translate this into something else. But yeah, if you want to have the classical picture, the frequency, amplitude, these are the different things. How rapidly it's oscillating, what amplitude it's oscillating with, and so on.
Sir, also some of the strings were circular and some were straight. So what is the difference between them?
Yeah, so the difference, these are called open and closed strings. Let me go back here. So these are what are called closed strings. As you can see, they are called closed because they have no boundaries. These, in fact, are common to all string theories. Okay, I described those 5 different string theories. All 5 different string theories have these closed strings. These are called open strings, right, which have open ends. And these are there only in one of the 5 string theories, which is called this is type 1 string theory. Let me go to that list. Yeah, so this theory over here has both open and closed strings. Okay? The open strings are the ones whose ends are not closed.
Good evening, sir. My question is that what is the relevance of shape of the strings, especially with the expanding pages of our universe?
Oh, the shape of the string basically tells us what the various particles are, okay, including the gravitons and how they interact. Okay. And that in turn determines the particular phase of the string tells us how what kind of theory of gravity we have, right? How they interact with matter, and depending on that, okay, the expansion of the universe comes. So it's not a direct relation. You have to go. I mean, you have to do several steps, right? There are a lot of equations in between. Starting from a particular compact space, you see how the strings are vibrating in that compact space. From that, you work out what kind of interactions the elementary particles will have, and you use that to figure out, right, what kind of expansion the corresponding universe will have. Okay, there are precise rules for doing that, but it's not just a one-step process, right? That you look at the shape of the vibrating string and you determine what kind of expansion the universe will have. But there are definite equations which let you do that.
So, would you once more explain the phases of universe with relevance to the expanding universe?
Yeah, so the phases of the universe are exactly the choice. Let me go back here. Yeah. So different phases of the universe just correspond to these different choices of the compact space scale. Okay? Because as I said, string theory is formulated in 9 dimensions, but 6 of the dimensions have to be small and compact in order to describe our world. So that choice is something that you have to make, and those choices correspond to the different phases. Okay? Once you have made that choice, okay, then the equations are completely determined. You have no further freedom. So once you have decided what this K is, you do your calculations and you find out how rapidly the phase will expand. Because it's basically the choice of the compact space that determines everything in string theory.
Good evening, sir.
Yes? Yeah, go ahead. Yeah, okay.
So my question is that how do you determine the size of this string? That is 10 to the power minus 33 centimeter cube.
Yeah, so this is determined from the strength of the gravitational force. Because as I said, string theory automatically contains gravity. Okay? And then you compare the strength of that gravitational interaction that comes from string theory with what you observe in nature. And that's what determines 10 to the minus 33 centimeter.
So you have told that this string actually mediates the gravitational force.
Yes.
So there is also a particle called graviton.
Yes.
So these are same or different actually?
Yeah, so the particle called graviton is what is responsible for mediating the gravitational force. Right? You remember that in the case of the standard model, I described the photon. Here. In this mediators, we have the gluons which are responsible for strong interactions, strong force. The photon that mediates electromagnetic force, and these mediate the weak force. In this list, you see that there is no particle that mediates gravitational force. Okay? And that's the reason why standard model doesn't contain gravity. String theory automatically gives a particle, which is the graviton, which mediates gravitational force. Right? That's so graviton is what is responsible for string theory mediating gravitational force.
Thank you, sir.
Sir, why it is that when we approach a black hole, the dimensions increase?
Yeah, so this again, we have to write the equations for the black hole. I mean, I have just given it in picture, right? But there are definite equations that you have to solve. And in that equation, so when you write down the equations for how the various quantities change as you move around the black hole, among those quantities will also be the radius of the extra dimensions, right? There are equations for those as well. And you find that the equations for the radius of the extra dimensions are such that as you approach the black hole, they start increasing. Right? It's just a particular solution to the equations that describe how the sizes evolve.
Thank you.
Hello, sir. Thank you for an intriguing lecture. I'm a physics student and I'll keep my question very simple. can I use statistical physics? Can I study statistical physics first and then jump into elementary particle physics? Is there a way to do that?
Yeah, we can do that. I have not described it here. Statistical physics is important when the universe is at a finite temperature. Okay? And we know that in our universe, right now it's also at a finite temperature, but it's very low, 2.73 Kelvin. But it was very much hotter earlier. Okay? So when you try to understand how the universe evolved from early times, statistical physics is very important. Right? You apply the laws of statistical mechanics to understand how we came to be what we are today.
Okay, sir. Sir, my second question is when you described something like compact space, is there a specific name for it, or is it called a compact space only?
Is there a specific name for it?
Yeah, to describe a compact space.
Well, the compact spaces that are normally used for string theory, which are relevant for, as I said, the simplest kind of compact space, six-dimensional compact space, is a product of 6 circles. Take each of the 6 directions to be circles. Okay? That's what I described for this in this black hole example. Okay? But the kind of compact spaces that are needed to describe what we see in nature, which brings us close to the standard model, okay, are what are called Calabi-Yau spaces. Right? They are particular kind of 6-dimensional compact spaces, right, which mathematicians have studied for various other reasons. And those turn out to be the ones that are most relevant for describing what we see in the standard model. The kind of particles that we see in the standard model come out when you use Calabi-Yau spaces.
Okay, sir. Sir, I have one more question. In your presentation, there was a line, even the fundamental constants of nature will appear to be different in different phases.
Yes.
What does that mean? What does that mean in very simple terms?
Yeah, okay. So what it means in the simple terms is, okay, let's go back to the example of ice and water. Okay. Now imagine that we didn't know anything about molecules and atoms, right? What constituents? You only had access to ice and water. And you measured the speed of light, speed of sound in ice and speed of sound in water. Okay. Now you might have thought that speed of sound is a fundamental constant, right? But if you measure it in water, you get one value. You measure it in ice, you get another value, right? So if you think of speed of sound as a fundamental constant, you will be led to conclude that they are different in ice and water. Okay. But of course, now we know that speed of sound is not a fundamental constant, right? It's derivable from the forces that act between H2O molecules, right? So similarly, at present, we think of the standard theory of elementary particles. You have the mass of the electron as a parameter, mass of quarks as parameters, right? The masses of W plus and W minus as another parameter, or equivalent to the mass of the Higgs as a parameter. So all of these you think of as some fundamental constants. Okay? But string theory has no fundamental constant. The only thing that it has is the choice of the compact space K. Okay? So if you take different choices of compact space, okay, you may get electrons of different masses. Right? But of course, the one that we need to identify as our universe is the one that gives the correct choice, mass of the electron. Okay? But in a different compact space, you may get particles like electron, but with a different mass. Right? That's the sense in which I said that the fundamental constants will appear to be different.
Sir, do you also think that translates to speed of light?
No, speed of light is something that is usually used to set the units. Okay? Because you see, when you compare theories, you can only compare dimensionless ratios. Okay? So you need 3 fundamental units that fixes the units of length, mass, and time. Okay? And we fix those units by the Newton's constant, the Newton's gravitational constant, okay, the Planck's constant h bar, and the speed of light. Okay. So you don't think those are variables anymore, right? Because those are the ones in terms of which you measure everything else. Okay. So in that sense, the speed of light you don't take as a fundamental constant. Okay. But all dimensionless quantities like the mass of the electron as measured in gravitational units, okay, is a fundamental constant.
Okay, sir. Thank you, sir.
Hello, sir.
Yes.
Good evening. So my question is that what is the current hypothesis on why these strings exist and what is the origin of strings? Means how did they originate? And is string theory also compatible with the current theory of origin of the universe? What is your opinion on
Yeah. So the point is, the origin of string theory, as I said, is very different. It was not designed to give a theory of gravity.
Not the origin of string theory, but how did the strings, means the physical manifestations of the strings came into existence, or is it assumed that they were always there in the universe? So this.
Okay, see in quantum theory, right, nothing is there forever, right? Things are getting created and destroyed all the time. So in the early universe, right, in the without string theory, if you think in just in terms of the standard model, okay, we can still use it to evolve, study what happened in the early universe till quite high temperature, not near the Big Bang, but till quite high temperature. And there, the particles are getting created and destroyed all the time. In string theory, those particles will be replaced by strings, right? So the strings will be getting created and destroyed all the time. Okay. Nevertheless, because the string size is so small, okay, they will be indistinguishable from particles, right? The way the consequences of string theory will differ from the consequences of normal particle theory will be at very, very high temperature near the Big Bang. Okay. Otherwise, the evolution of the universe will be exactly as we study in a theory of elementary particles.
So my first question is, if strings are in one dimension, then why not see them in accelerators?
Why not?
See them in accelerators.
Yeah, the reason that we don't see them in the accelerators is what I described here. Let me go back. Yeah. The typical size of a string, right, that you can estimate is 10 to the minus 33 centimeters. Okay. And in current accelerators, we can only see structure of 10 to the minus 17 centimeters. Yeah. If you could increase the energy of the accelerator, okay, so that you can probe a distance of 10 to the minus 33 centimeters, we'll definitely be able to have to see strings. Right? If you don't see strings, then you have to declare that the theory is not the right theory of the world. But with current accelerators, you cannot see it simply because strings are too small.
Sir, my second question is, why does it predict zillions of universe but not exactly ours? How do hidden dimensions stay tiny without breaking everyday physics?
Sorry, I didn't get the question. Can you repeat?
My question is, why does it predict zillions of universe but not exactly ours? How do hidden dimensions stay tiny without breaking everyday physics? Actually, I want to say that why these tiny things are existing in our universe without breaking the law of the physics, everyday physics, actually. Yeah.
That if the size of the string is really so small, right, 10 to the minus 33 centimeter,
yeah,
then everyday physics will not see the strings as strings, right? They will just see them as particles. So what about the particle theory predicts for everyday physics will also be predicted by string theory. Yeah, but this of course relies on the big assumption that we'll be able to find a phase that gives us the standard model particles. Once we have find a particular choice of k that reduces string theory to the standard model particles, then the deviation from the laws of standard model will come only when you can probe distances of the order of 10 to the minus 33 centimeters. And everyday physics doesn't probe distances of this kind. Right? That's the reason the everyday physics is insensitive to the fact that the elementary particles are strings.
So my last question is that if string theory actually exists, then if it breaks, then what will be happened?
If it
breaks? Yeah.
Strings normally cannot break. Okay. So I described that that there are these closed strings and open strings. 4 of the 5 string theories have only closed strings, they don't have open strings. There the string cannot break. Right? The laws of string theory doesn't allow you to break, for a string to break. In the 5th one, which has both closed and open strings, there is indeed a way for a string to break. A closed strings can become 2 open strings. Okay? And this is in fact one of the ways the strings can interact with each other. Right? A closed string can break into 2 open strings, then 2 open strings can join and make another closed string and so on. So this is part of how interaction takes place in string.
Thank you, sir.
Sir, this minus 33 centimeter is the limit because of the gravitational force.
Yes.
Is there a limit that we can have only 9 dimensions in string theory?
Yeah, so that is hard to explain why that is the case. But I had to formulate the theory and check the various mathematical consistencies. Right? You find that you can formulate it only in 9 dimensions. That if it's not in 9 dimensions, then the theory just doesn't make sense. Okay? It is very strange because this is not the way quantum field theory works. The theory of point particles can be formulated in various dimensions. But that is not the case in string theory. Okay. Yeah, but this is something we cannot explain in words. I mean, yeah, you have to actually write some equations and then you see that some terms in the equation just do not cancel, okay, unless you choose 9 dimensions.
Good evening, sir. So my question is, you give different examples of different phases of how we can go to different phases and experience the 9-dimensional space and other several dimensional space. So, sir, what was the exact use of string in the string theory? What does it exactly conclude about the string, sir? How is the string helping us to know this theory?
Yeah, because if you don't have strings, okay, then you cannot write a quantum theory of gravity in the first place. Right? That's the main problem. So if you cannot even write a quantum theory of gravity, right, then all these studies become meaningless. Right? So that's where the string theory comes in. Right? String theory tells us that it's a consistent quantum theory of gravity, and now within that theory, you study these various possibilities.
So my second question is, so what does it exactly conclude on its own? Because, sir, it helps us to understand the black hole and quantum fields theory, but what exactly prove on its own, sir?
What exactly does it do on its own? Well, if you mean what is how can we distinguish string theory from particles?
Yes.
Okay? And that will be, if you can probe distances of the order of 10 to the minus 33 centimeter, okay, then all the elementary particles, or what we think of as elementary particles, should show this string-like structure. That's what it does it on its own, right? This is a signature of the theory, right? That is universally valid, right? Doesn't depend on what kind of compact space K you have, right? And so it's a universal property of string theory that if you probe distances at that order, 10 to the minus 33 centimeter, you will see all the elementary particles having string-like structure.
Sir, you have mentioned on your slides ADS-CFT. What does it actually mean?
Okay, what does it actually mean? It basically means, let me go back to that slide. Yeah, so it means that, as I said, the string, so if you look at this picture, right, here I had shown 5 different windows, right? That these are the windows through which you can view different phases of the theory. ADS-CFT, that is like another window. Okay, imagine that a 6th window has opened up. And with that window, that allows you to study some other phases of the string, okay, very well. So this is a technical word, ADS-CFT. ADS stands for anti-de Sitter space, so that refers to what kind of string theory you have. String theory you have to put in a particular space called anti-de Sitter space. And CFT stands for conformal field theory. It's a particular class of theories of point particles. And the idea is that if you put string theory on this kind of spaces, if you choose K to be like, and part of K to be, not part of K, but the full space time, if it has this anti-de Sitter space, then it can be described in terms of a theory of point particles. Okay? So that's like opening another window, because you imagine there is another window through which you can study string theory, and that's this, ADS-CFT. Right? ADS-CFT stands for one particular way of studying string theory using the theory of point particles.
So how does boundary CFT know bulk black holes?
Well, how does it know? You have to attend this conference, I think, because that's a long story. But indeed, the point is that the idea is that the black holes in anti-de Sitter space are represented by thermal state in the boundary theory. Okay, so if you have a finite temperature state in the boundary theory, that corresponds to black holes in anti-de Sitter space in the bulk. But more than that, I think you really need to attend the conference.
So if strings are 1D, then why are not they seen in accelerators?
That's essentially because the size of the string is very small, right? Because you see the size of the string is of the order of 10 to the minus 33 centimeter, and the accelerators simply cannot see that kind of distance. Yeah. Current accelerators can only see up to 10 to the minus 17 centimeter, right? 10 to the minus 33 centimeters. This is much smaller than 10 to the minus 17 centimeters. Okay? So you really have to increase the energies in the accelerators to be able to see distances of this kind. But if you do manage to do it, then one has to either see this string structure or you have to declare that string theory cannot be the right theory of the particle.
One last question.
One last question from me. Is it okay?
Yeah, okay.
So, this is one thing, temperament, the spatial dimension.
Yes.
What are other properties, like charge, mass, they can be measured?
Yeah. So,
we don't have to depend on one particular dimension.
no. So the point is, once you have chosen a K, right, that tells you not just the masses of the particles, it tells us what kind of charge this particle carries, what kind of interaction it has, and it tells you everything about the theory. Right? So once you have identified a particular phase of the theory, you can calculate anything that you like in that theory. Right? The masses of elementary particles, the charges, the interactions, and so on. But the real question is, does that agree with what you have seen in experiment? Right? And the phases that you have found so far do not agree. Right? They come close qualitatively, but not quantitatively. Right? And that's the main challenge. So, but given a phase, you have everything. Right? Mass, charge, interactions, and everything is determined.
Hello, sir. Good evening. Yes. Sir, I have a very fundamental question. Is strings, is it correct to say that strings are the localization of certain type of wave functions? Or we can say strings and the concept of wave function as we understand in quantum mechanics are entirely different?
No, you can think of the strings as being described by wave function. Just like particles have wave function, what does it mean? That it tells us that what is the probability of finding a particle in some region. Right? The wave function of the string will tell us what is the probability of finding the string in a certain region but with a given shape. Right? In this, suppose you take a string of this kind, a particular shape in space. Wave function tells you what is the probability that you will find a string there in that form. Right? You take a different shape, the wave function tells you what is the probability of finding the string in that shape. That's the way you do quantum mechanics of strings. So instead of talking about just wave function as a function of the position, right, as a single variable, here you have to describe the wave function as a function of the loop, because that sort of describes the whole string.
Okay, sir. Thank you.
Good evening, sir. Sir, I just had a doubt regarding the size of the string. Is
Yes.
that it's 10 to the power minus 33 centimeters, and we have defined Planck length as approximately 10 to the power minus 35 centimeters. So how are we?
No, minus 35 meters. So this is basically Planck length.
Yeah. Okay. So basically we are relating strings with the size of the Planck length.
Exactly. Yeah.
And I just had a doubt regarding the bubbles. If we are defining the phases as bubbles, can we say that they depend upon the physical quantities of the rapidly expanding universe?
Okay. See, it's not that the phases are bubbles. Right? Phases are phases that form as bubbles inside something. Right? Again, you think of supercooled water. Okay? So, if in a supercooled water, right, what will happen is if you just disturb, suppose you have a small nucleation center, right, then ice will start forming around the nucleation center. Okay? And then that ice will start expanding inside water, right, because that's a more stable phase. Okay? So, this ice that is expanding, that is what we are calling the bubble. Okay, so, but that is not that, it's not that property of that is provided by the property of the water, intervening medium. Right? Ice has its own intrinsic property. Okay? But because it's more stable than the water, right, it starts expanding.
And sir, is this how we can prove that inside a phase there will be different phases forming?
So this is quantum mechanics, right? That you can use laws of quantum mechanics. It's like quantum mechanical tunneling. Right? So if you have, say, a potential 2 minimum, we know how to calculate the tunneling probability from one minimum to another minimum. Right? Suppose the second minimum is at a lower value. Right? There is a tunneling probability. So it's exactly that kind of calculation that tells you what is the probability of forming a particular phase inside another phase.
Thank you, sir.
Let's all thank Professor Sen for patiently answering questions and a beautiful lecture. I would like to request our director, Professor Karmalkar, to kindly come on stage and felicitate the Thank you very much for all the participants for coming here from great distances, students for their very enthusiastic participation. And if you have more questions, Professor Sen has a lot of patience. You will run out of patience, but he has a lot of patience. You can ask him outside. I would like to thank Professor Sen actually for taking time out of his schedule and giving a nice lecture here. Our director, Professor Karmalkar, and many of the functionaries of the institute who extended their support for not just this public lecture, but during the last 1 week for the organization of the conference, and all my colleagues, students, faculty, staff, everybody who contributed. Thank you very much and have a nice evening.